In this video, I will discuss a JEE Advanced PYQ from topics EMI and LR circuit. First, I will discuss some basics. If you consider a closed loop, EMF induced in this loop is rate of change of flux linking the circuit. There will be some magnetic field in some direction. So the flux linking the circuit is the magnetic field into the area. So the induced EMF is, this is Faraday's law of electromagnetic induction. Now consider this particular circuit. I have horizontal conducting rail and there is a conducting rod and the length between these 2 points is say L. Okay, and this rod is say moving inwards with a velocity V and there is a magnetic field say in this direction. It's a uniform magnetic field. So the rod is moving in, the flux within this closed path is changing. It's actually decreasing because area is decreasing. So there will be induced EMF in this loop. It's d phi by dt by Faraday's law of electromagnetic induction, and the flux is the uniform magnetic field into the area of this thing. Let this portion of the moving rod at any given instant be x. So this rectangular area is L into x. So area is L into x. B is uniform and constant magnetic field. L is also not changing. The length of this portion, it's a horizontal ray. So this will become B into L into dx by dt, which is the velocity of this rod. X is the velocity of this point, which is same as the velocity of this rod. So we get the result that the EMF induced in this closed loop is B into L into V. Another basic concept is LR circuit transient. Suppose I have a circuit like this, resistor and an inductor, and there is a switch here and a DC source of EMF E. So as soon as switch is closed, at time t equal to 0, the current will start flowing. How will the current change as a function of time? So you can write KVL in this loop. So the drop from here to here is I into R, where R is resistance value, let the inductance be L, and drop across the inductance is L into di by dt. That's equal to the induced cell voltage, which is E. This comes from d phi by dt, and flux is proportional to the current, and the constant proportionality is I. So flux is L into I. So d phi by dt will give me di by dt into L because L is constant. So here it's a differential equation, independent variables t and the dependent variables current I. So you can solve it. So this will become E minus IR by L equal to di by dt. So the simple differential equation, it's di by E minus IR equal to dt or I can take R by L outside. So this will become, or we can just keep it like that. Okay, so integrate both the sides during the time 0 to t, and the current at the time t equal to 0, or 0 minus is 0, and at time t let it be I as a function of time. So this is ln divided by derivative of this with respect to the current minus R by L, and you have to put the limits 0 to I, and the right hand side integration is just t. Between the limit 0 and t, so it will become t. So take this thing to the other side and putting the limits. So now taking e to that side will become 1 minus I into so this will give me the final thing I as a function of time as 1 minus e to the power into e by r. So this is how the e varies the function of time. So if you plot this current I as a function of time at t equal to 0, current will be 0. At t equal to infinity, it's minus infinity, so this thing is 0, so it will become e by r. This value is e by r. So the current will rise exponentially like this and saturate at e by r value. So with this understanding, you can solve this JEE Advanced question. Timestamps are given in the description box. You can watch parts of video if you're running short of time. This is the question. A 10 cm long, perfectly conducting wire PQ is moving with a velocity 1 cm per second on a pair of horizontal rails of zero resistance. One set of the rails is connected to an inductor L, 1 microhenry, and a resistance R, 1 ohm, as shown in the figure. The horizontal rails L and R lie in the same plane with a uniform magnetic field B equal to 1 Tesla perpendicular to the plane. If the key is S is closed at a certain instant, the current in the circuit after 1 millisecond is x into 10 to the minus 3 amps, where the value of x is dash. Assume the velocity of the wire PQ remains constant 1 centimeter per second after key S is closed. Given e raised to the power minus 1 is 0.37, where e is base of the natural logarithm. You can pause and run this question. So we'll use the result. This rod is moving on horizontal rails. So the EMF induced will be BLV. Magnetic field is 1 Tesla. Length into velocity is 1 centimeter per second. So it will be 10 raised to minus 2 in SI units, centimeter meter conversion. So this much is the induced EMF. 10 centimeter. So L is 10 centimeter, that's 0.1 meter. So it's 10 raised to minus 3 volts or 1 millivolt. So this is the EMF induced across this rod. So when the switch is closed, the current will rise exponentially as I equal to I naught into 1 raised to the EMF minus T by tau, where tau is the time constant, it's L by R. I naught is the saturation value of the current, which is the induced EMF by R. At very large time, this inductor will act as a plain wire. So the current is disturbed by this voltage and this thing. So induced EMF is 1 millivolt and the resistance value is 1 ohm into 1 minus e to the power minus t, and tau value, which is L by R. L is 1 milli and R is 1. So it's 1 millisecond. So this is 10 raised to minus 3 into 1 minus. You have to find the current at 1 millisecond. After 1 millisecond, that you have to put t as 1 millisecond. So it will become e raised to the power minus 1. E raised to the power minus 1 is 0.37. So 1 minus 0.37 is 0.63. So current is x into 10 raised to minus 6. That means x is 0.63. So the answer to the question is x is 0.63. That is the correct answer. This is what is done here. EMF across this thing is BLV. This is across the full length from BLV. So that's 1 millivolt. And time constant of this RL circuit is L by R, which is L is 1 millihenry and R is 1. So it's 1 millisecond. So I will exponential raise as I naught into 1 minus e to the power t by time constant. So the I naught is E by R. E is 1 millivolt and R is 1 and tau is 1 millisecond. And you have to find the current at 1 millisecond. So it becomes e to the power minus 1. And 1 by E is given as 0.37. So answer is 0.63 milliamps.